In this skill, we're again trying to find the pH of a mixture of an acid and a base. This time we're going to have equimolar amounts of our acid and base so that they react completely with each other. One of them is going to be weak and one of them is going to be strong. So in this question, we have 7.26 moles of hydrofluoric acid solution. That's a weak acid, mixed with 3.63 moles of calcium hydroxide solution. That's a strong base at 25 degrees C. We're told the total volume of the solution is 1.01 liters. We can see in our molecular equation, we've got all our reactants and products shown. In the net ionic equation, since calcium hydroxide is a strong base, it's going to dissociate into its ions, and the calcium 2 plus ion would appear on both the left and the right of our equation. So that gets cancelled out because it's a spectator ion, and we're just left with our participator ions here. Now we know that we have an equimolar reaction happening. That means our acid and base are going to react completely together. Our first step is figuring out how many moles of our weak acid and its conjugate base will remain after the reaction happens. So we started out with 7.26 moles of HF and 3.63 moles of calcium hydroxide. We can see in the equation we have 2 moles of HF reacting with 1 mole of calcium hydroxide. So that's why we have twice as much hydrofluoric acid as we do calcium hydroxide to start with, because we have a 2-to-1 ratio. Then we're going to produce calcium fluoride, and the ratio for that is 1 mole of calcium fluoride produced for 1 mole of calcium hydroxide. So that means the amount that we produce is going to be 3.63 moles of calcium fluoride produced. We need to figure out how many moles of fluoride ions are going to be produced. Remember, calcium fluoride is made up of Ca2 plus and 2 F minus ions. So that means that in the end, we're going to have 2 times 3.63 moles of F minus ions, which is 7.26 moles of F minus ions. So let's go ahead and fill that in here. We know that all of our hydrofluoric acid got reacted, so we're going to have 0 left of that, and we know that that produced 7.26 moles of F minus ions. We also need to know their concentrations. Let's head to the reference sheet to find the equation for that. Here's the solutions page on the reference sheet. Here's the molarity equation. Molarity is equal to number of moles divided by volume. Molarity equals the number of moles divided by the volume. For hydrofluoric acid, since we had 0 moles, we know that our concentration or our molarity is also going to be 0. For fluoride ions, we know that we have 7.26 moles of fluoride ions, and our volume is 1.01 liters of solution. So that's going to get us a molarity of 7.19 molar. So we can go ahead and fill that in here. Our hydroxide ions reacted fully with the H plus to form H2O. So we don't have any excess hydroxide or hydrogen ions in our solution, causing it to be acidic or basic. However, at the end, we do have this F minus ion. Now, HF, that is our weak acid, and F minus is our conjugate base of that weak acid. And remember, the conjugate base of a weak acid itself acts as a base when it's in water, because some of the F minus will react with the water to form hydrofluoric acid and OH minus. So as a result, because we have this weak acid forming this conjugate base in the end, we're going to have a slightly basic solution because some of that base is going to react with water to form OH minus. So we're going to figure that out using ice tables. So that's what we're told here. The F- produced reacts with water according to this equation here, which is exactly what we just discussed. And we've been given Kb, the base dissociation constant. Let's find an expression for the base dissociation constant for this reaction here. Here's the acids and bases tab of the reference sheet, and here's our base dissociation constant Kb. It's the concentration of OH- ions multiplied by the concentration of the conjugate acid divided by the concentration of the base. So Kb is the concentration of OH- times the concentration of the conjugate acid divided by the concentration of the base. Now looking at this equation here, this is now going to be our base, and HF is now going to be our conjugate acid. So to fill in these here, OH- is just OH-, our conjugate acid is HF, and our base is F-. Another way to think of this is that it's exactly the same as the equilibrium constant equation. On the top of our fraction, we have our products, HF and OH-. On the bottom, we have our reactants, F-, and H2O doesn't appear because it's a liquid, and we only have gases and solutions appearing in our equilibrium constant expression. So there's our base dissociation constant, Kb. So let's go ahead and fill that in here. We had OH- and HF on the top, and we had F- on the bottom. Next, we're going to complete the ice table for this base. So the initial concentration, that's immediately after the reaction has taken place. So we already calculated that up here. Immediately after the reaction has taken place, the concentration of F- ions is going to be 7.19 molar, because that's what was produced in our reaction. And to start with, we don't have any HF because that has all been used up. And we don't have any OH- since we didn't have anything in excess. So those are our initial concentrations. We need to figure out our equilibrium concentrations. To do that, we're going to write an expression for our change in concentration in terms of X. And looking at our equation here, if F- got used up, that would be minus X for F-. We're going to produce one HF and one OH-. So that gives us a change in concentration of negative X for F-, positive X for HF, and positive X for OH-. That's going to leave us with an equilibrium concentration where we add together our initial and our change. So it's going to be 7.19 minus X for F-. It's going to be 0 plus X, which is just X for HF, and 0 plus X, which again is just X for OH-. Now we're also going to use the small x approximation. Remember, when X is really small, which it's going to be because we have a really small Kb here, the result is that when we subtract or add that X to a big number like 7.19, it's not going to have any effect on that number because it's so small that when we add it, we're going to get exactly the same number to three significant figures. So what we're going to do is just get rid of the minus X here. And we're just going to assume the X is so small, it's not going to affect 7.19 when we subtract it. That's going to make our calculations a lot more simple. So I now have an expression for my equilibrium concentrations. I also know my Kb values, so I can plug that all into my Kb equation here. So Kb, we're given in the question, that is 1.59 times 10 to the power of negative 11. Then we have the concentration of OH-, which we have written as X. Then we have the concentration of HF, which we've also written as X, and we're dividing that by the concentration of F-, which is 7.19. So I'm going to multiply by 7.19 on both sides to get rid of that on the right. And I'm going to change X times X to just say X squared. Now I know that in order to solve this equation, I just need to square root both sides, so that's going to give me X is equal to the square root of 7.19 times 1.59 times 10 to the power of negative 11. So I'm going to go ahead and put that in my calculator. That gets me an X value of 1.07 times 10 to the power of -5. So we can go ahead and fill that in our change in concentration row. We know the change is -x for F minus ions. So we're going to have -1.07 times 10 to the power of is written as E on this platform, -5. And it's going to be positive for our HF concentration and our OH minus concentration. Then for our equilibrium concentrations, for HF and OH minus, it's going to be the same thing because it started with 0. So our equilibrium concentrations here are 1.07 times 10 to the power of -5. And for F minus, we use that small x approximation, but let's just check that. If we had have done 7.19 minus 1.07 times 10 to the power of -5, if you just put that into your calculator, you're going to end up getting 7.19 to 3 significant figures. So that shows you that the small x approximation worked well, because even when we add that change in by subtracting that number, it doesn't affect our number to 3 significant figures. So our answer here is just 7.19. Finally, we need to find the pH of our solution. We know the concentration of hydroxide ions at equilibrium, so we can use that to figure out the pOH. Here's our equation for pOH. It's pOH is equal to -log the concentration of OH minus ions. So we've got pOH is equal to -log the concentration of OH minus ions. So we can go ahead and put in our numbers there. -log the concentration of OH minus ions at equilibrium we just calculated is 1.07 times 10 to the power of -5. So if we put that into our calculator, we're going to get a pOH of 4.97. Let's go ahead and fill that in. Awesome. So last step is to find the pH of the solution. If we know the pOH, we can find the pH using our equation. It's this one here. It converts between pH and pOH when we're at 25 degrees C, which we are in this question. We were told at the beginning. So we have pH plus pOH is equal to 14. We're trying to find pH, so I'm going to subtract pOH from both sides so that gets cancelled out on the left, leaving us with pH is equal to 14 minus pOH. So let's put in our numbers. pH is equal to 14 minus, we just calculated pOH is 4.97. So if I put that into my calculator, that gets me a pH of 9.03. So let's go ahead and fill that in over here. Awesome. So there was a lot going on in this question. We had a lot of different steps. We had an equimolar acid-base reaction where our acid and base reacted completely with each other. However, because we had one strong and one weak, that means that one of the ions produced the conjugate acid or conjugate base of the weak base or acid that we started with is going to end up reacting with the water to form some H plus or OH minus ions. So that's why we had to use the base dissociation constant and an ice table to figure out what the equilibrium concentration of H plus or OH minus ions would be for the given conjugate acid or conjugate base. And then we could use the equilibrium concentration of OH minus or H plus ions to figure out the pH or pOH in the end.